So let's do a different kind of example. This is one based on the textbook by Carter, problem 12.8. Isolated system has energy levels 0, epsilon, 2 epsilon. Epsilon is some energy difference. The total energy of the system is fixed at 2 epsilon. 4 distinguishable particles are placed in the system. Calculate the entropy of the system. So let's process it a little bit. We've got these energy levels. Total energy of the system is fixed, 2 epsilon. 4 distinguishable particles. Calculate the entropy of the system. That's what I'm trying to find. Okay, so clearly I'm going to try to use this formula, Kb, natural log of omega, where omega is the multiplicity of the system, or the number of microstates that lead to this overall macrostate. And now we have to calculate what omega is. So the first thing I'll do is I'll start by drawing out the energy levels. So there are the energy levels. And now I got to put these 4 particles, A, B, C, D, in the system. So where could I put them? You might start by thinking, oh, what if I just put them all in the lowest state? But that would not meet this constraint here. So remember that the total energy of the system has to add up to 2 epsilon. So having them all down at the bottom is not going to work because the total energy would be 0. And I need the total energy added to 2 epsilon. So one way to do that is to have 2 of them here and 2 of them here, right? These 2 in this level here give me the 2 epsilon. And the other 2 contribute 0. So this is one way to arrange it. I'm going to call this macrostate K. K is equal to 1. I'm just going to call this K equals 1. But that's not the only way to arrange them. Can you think of another way to arrange it? Go ahead and pause the video and see if you can come up with another way of arranging them. Okay, did you think of another way? So if I have my 3 energy levels here, 0, epsilon, 2 epsilon, hopefully you found this way. I could have 1 up here and the other 3 down here. Okay, so the one up top there gives me my 2 epsilon of energy, and then the other 3 don't contribute anything to the total energy. Total energy is still 2 epsilon. Okay, now I have to think about the number of microstates in here. So this one I'll call macrostate. K is equal to 2. So K is equal to 2. So I've got those 2 macrostates, and I have to think about the number of microstates. So how many ways can I arrange the 4 particles A, B, C, D to give me macrostate K equals 1 and macrostate K equals 2? Okay. This one, the one on the right here, is pretty easy. So what is omega K? Let's call it omega 2, the multiplicity, number of ways to arrange this. Not too hard to figure out, because you could have A up at the top and then you could have B, C, D down at the bottom, or you could have B up at the top and A, C, D down at the bottom, and you get the idea. You could have C up at the top or you could have D up at the top. So what you're choosing is you're taking those 4 particles and you're picking one of them to be in the top state. So I'm choosing here, this is 4, choose 1, right? I chose the 1 to be at the top state, and then the other 3 are by default left in the bottom. 4, choose 1, well, hopefully you know it's just 4, but let's use the formula. That's 4 factorial over 4 minus 1 factorial times 1 factorial. So that's 4 factorial over 3 factorial, which is 4. Okay, so there's 4 ways of doing this. Okay. Go ahead and pause the video and think, can you determine what is omega 1? What is the number of microstates for this state on the left here, the macrostate on the left there? Okay, so not too hard. Basically, it's the same idea. I take the 4 particles A, B, C, D, and I pick 2 of them, and I put them in the state epsilon. So to determine this one, I should choose 4, choose 2. Take my 4 particles, pick 2 of them to be in the upper state, and then by default the other 2 are in the lower state. So it's 4 choose 2, and that's 4 factorial over 4 minus 2 factorial times 2 factorial. This turns out to be 6. Okay. So let's make a little table to kind of analyze this system. Okay, just summarizing the microstates of this system, I've got the macrostates of the system. I've got 2 of them, k equals 1 and k equals 2. Those are just labels for the system. So labels for the state. So k equals 1 the macrostate at k equals 1, it looks different than the macrostate k equals 2. So the macrostate k here, I'm calling this one state 1, and this one state 2. That's just what I'm labeling the states. And then we calculated the number of microstates that lead to the macrostate k equals 1. And there were 6 of these, and there were 4 of these. That was done on the previous slide. So if I add these up, I get the total microstates is 10. Add them up. And then I can answer my question. S is equal to kb natural log of omega. That's the total number of microstates in the system, the multiplicity of the system. So S is going to be kb natural log of 10. That'll be the final answer to this question. Just a different question, which you might be asked on similar different questions, is you could ask, what's the probability that each one of these occurs? Remember this, to get the probability, you just take the multiplicity divided by the total multiplicity. So all of these microstates, all 6 and all 4 of these, so all 10 of those are equally likely. That was the assumption in an isolated system. So the probability here would be 6 out of 10, 60%. And the probability here would be 4 out of 10, which is 40%. So this one occurs a bit more often than this one. Okay. So there's an example of how to calculate entropy and probabilities using a system which has discrete energy levels distributing the distinguishable particles through the energy levels. Very important to respect this constraint. So we had to respect the total energy was fixed here as an isolated system. So the energy couldn't change. The particles can move between the levels, but the total energy can't change. So just to summarize this topic, the main formula that we've added is this one, the relationship between entropy and number of microstates, or entropy and multiplicity. S is kb natural log of omega. That's the formula that's on Boltzmann's tombstone and was one of his main contributions to physics. So just to remind you, in an isolated system, all microstates are equally likely to occur. The second law of thermodynamics says that the entropy of an isolated system will tend to increase over time until equilibrium is reached. So what that's saying is that if the entropy is always increasing, that means you're moving to macrostates which have a higher and higher multiplicity. Right? If the left-hand side of that formula S is going up, that means the right-hand side is going up, and the only way to do that is to increase the multiplicity, omega. So the second law of thermodynamics is saying that you're going towards states which have higher multiplicity, and that makes sense because those states are more likely to occur. So what you're doing and what you're ending up in, the equilibrium state, is the one with the highest multiplicity. You're ending up in the state which is most likely to occur. That's how we understand the second law of thermodynamics from a microscopic standpoint. Okay, so what we have to do next in the course is we have to move beyond this isolated system here. So far we've been talking about isolated system, but what if I want to think about a system which is in contact with some other system? How do I handle the microstates in that system? So it's going to turn out that if you're in contact with a reservoir at some temperature, the microstates are no longer going to be equally likely to occur, and we need to think about how to handle that. So that's where we're going next.